All right, here we are back again with the integral test and the p-series and taking a look at example number 2. This time we're going to determine convergence or divergence of a series using the convergence of p-series theorem. So with this particular theorem, it says some stuff. And before we get into the stuff that it says, I want to take a look at several other things. Of course, we've got our p-series, and a p-series is going to be represented by this summation formula right here. We've got 1 over n to the p, and p has to be a positive constant. So no matter what, p is positive. Now there's a special form of the p-series called the harmonic series. And the harmonic series is just represented by this 1 over n. And of course that's going to generate this list of terms here, but that's a p-series when p has a value of 1. So when p is 1, that's called the harmonic series. But the general harmonic series, so a very general harmonic series, is going to be this guy right here. 1 over a to the n plus b. Now when we take a look at the convergence of p-series theorem, what this says is that, alright, so you got this p-series going on. Now p's got to be greater than 0. Okay, you can't have a negative exponent. And then this is going to do one of two things. If p is bigger than 1, then our series is going to converge. However, if our value of p is going to be between 0 and less than or equal to 1, then our series is going to diverge. So basically what you have to do with this kind of stuff, it's almost too easy. You're just going to have to analyze the value of p. So let's go ahead and take a look at our 3 examples. So here in example 2a, we've got to take a look at this guy right here. And of course in that particular formula, you want to recognize that first of all that it is a p-series, and the value of p is what? Oh, that's right, 4 over 3. Now 4/3, how does that compare to 1? Of course it's greater than 1. So what does that mean? This series is going to converge by the convergence of p-series theorem. So here we go, we're taking a look at example 2b. So for this particular series, okay, we're not given the formula. Like in A, we were given the formula, but in B and C, we're just given terms. So we kind of have to work backwards a little bit to figure out what the formula is. And for B, all right, each one of these numbers in the denominator, 4, 9, 16, 25. So this is our second term, our third term, our fourth term, and our fifth term right here. And of course, 1 is our first term. So what's the relationship between the term number and the denominator for these? What? That's right. The denominator is the number squared, the term number squared. So that means we would have this for our formula, written in series notation, n equals 1 to infinity. So that is going to be 1 over n squared. Ooh, well then what's that tell us about our p-value? Our p-value is going to be 2, which is of course greater than 1. So that means what kind of conclusion are we going to have? Same as choice A. The series converges by the convergence of p-series theorem. So we would write that again for example B. Now, for example C, again, we're given the terms. We're not actually given what the summation formula is. So we've got to kind of play around with that. But similar to the previous one, we've got 4 being cubed rooted. We've got 9 being cubed rooted. We've got 16 being cubed rooted, and so on and so forth. So again, this is my first term, second term, third term, fourth term, and fifth term. And notice the expression for each one of these is going to come up with, you're going to start with n equals 1, go to infinity, and we've got 2. If you square that, you get 4. If 3 squared, of course, will be 9. 4 squared is 16. But you've got this cube root piece. So that means you're going to have 1 over n to the 2/3 power. So again, we're going to analyze the p-value, which is just the exponent, and the exponent is 2/3. So if p has a value of 2/3, how does that compare to 1? Well, that is less than 1. So that means, in this case, our series is going to diverge by the convergence of p-series theorem. So here's 3 different examples of using the convergence of a piece of the p-series theorem, and hopefully by now you can recognize determining the value of p helps you figure this out. And sometimes you're given the formula, like in example A, and other times you actually have to work a little bit backwards and come up with the formula for the summation, as in examples B and C. But in either case, you analyze the value of P, and then that tells you whether the series converges or diverges. Alright, that's it for this video. Thanks for watching these quick examples, and I will see you guys soon for example 3.